Welcome to the 7th module, Correlation and Linear Regression. This is just the basics. So what we're planning to do is take a look at whether or not two variables have an association that mimics a linear relationship. And we assess that by the correlation coefficient R, which gives us the strength and direction of that relationship. Now, as a caveat, I work with variables in the social sciences, which you've seen throughout this statistics portion, right? I like personality variables, for example, is one thing I've studied a lot. And in those areas, these correlations make sense. In other research areas, a different strength of correlation chart might be appropriate. So again, this is probably appropriate for most social science settings, psychology, education, marketing research, that type of thing, anything in the social sciences. So we're going to say that the correlation is strong when an absolute value it's above 0.75. So a negative 0.8 and a positive 0.8 have the same strength of correlation. Moderate will be between 0.5 and 0.75, and so on. And if we're below a correlation of 0.25, in many cases we're going to say we have little or no correlation. The topics we're going to cover today are going to go with two examples. In the first example, we're going to talk about correlation and how to build a linear model. We're going to do the regression statistics and analysis. In example 2, we're going to kind of ramp it up a little bit, and we're going to see if we can use a t-test here to test the significance of correlation or the significance of the slope. And we're also going to talk about the possibility of using some randomized approaches for linear regression. So, shocking empathy. So our first example cracks me up. So just listen to the setup here. They're doing a psychological test, and they're going to deliver an electric shock to the significant other of 14 women, and the woman has to watch the significant other being shocked. And so prior to this, they've measured the woman's empathy levels, some kind of, personality variable type. Likert scale questionnaire has established her level of empathy. And then what they're doing is they're measuring where she would actually be experiencing physical pain, right? So the part of her brain that would be active if she were in pain, that's where they're measuring. They've got like electrodes attached to her head or something, and they're going to be measuring that activity level in the pain center of her brain. And so the question is, do higher empathy levels correlate with a higher pain activity levels when watching the significant other be hurt? And that's all fine and good, except it's hilarious. As a human subjects researcher myself, there's just all kinds of problems with ethical treatment of human subjects that are potential problems. It would take a lot to get this study done these days, but this is what cracks me up. In the first observation, we see somebody who has less pain activity in that part of their brain rather than more. So that's kind of funny. Was she angry with the significant other? Was there a fight recently? So the setup cracks me up, and that first data point cracks me up. But let's take a look at how to assess the correlation. So we're using a linear model, and that comes with the assumption that we have an independent variable and a dependent variable. In this particular example, the independent variable is empathy, because the researchers' hypothesis is they believe higher levels of empathy will lead to higher activity levels in the pain center of the brain when the women see their significant other shocked. So think about it in a situation where you have a father's height and a daughter's height, right? Obviously, one of them needs to be the independent variable. Genetics get passed in one direction, so the father's height would be the independent variable and the daughter's height would be the dependent variable, because the daughter's height would depend on the father's height. Now, in some examples, it doesn't particularly matter which one is which, but along with this linear model comes sort of the implicit assumption that one variable is driving the other. All right, so we're going to take this data and enter it into our graphing calculator. So you hit the stats button on your graphing calculator, and the very thing that pops up is this. There's an edit menu, calc menu, and the test menu. And we're going to choose the edit menu. And we're going to enter our X data into list 1 and our Y data into list 2. So for us, this will be empathy in L1 and pain in L2. So the first thing we're going to do is verification, right? We can't build a linear model unless there appears to be some linear association between the two variables. So we're going to do that with a scatter plot. So if you go to second y equals on your graphing calculator, you can go into your stat plot menu, and you can see that I've got L1, it actually asks for the X list in L1. I put my Y variable in L2 because I was anticipating this setup, right? And while I'm not claiming the association is extremely strong, you might be able to convince yourself, however, that there's a linear pattern in this scatter plot. I'll admit that some of these points down here and these points out here are pretty big outliers if there is a linear association. So we aren't expecting a high correlation. This is certainly not a correlation that's even probably 0.5 or 0.6, right? It's probably a weak association at best. Real world data that I use is often really messy, and so that's kind of a downside to using real world data. But let's take a look. It's fun data to work with. And I just want to point out that this is Zoom 9. Zoom 9 is the Zoom stats feature. We use it all the time. And make sure that you learn how to do that because it will take whatever stat plots are active and it will zoom in on the range of data for the lists that are associated with those active stat plots. So you definitely want to remember this Zoom 9 feature. We've tentatively decided to proceed with this analysis. Again, you can argue about the linearity in that scatter plot. The key thing was we didn't see a specific nonlinear pattern that would fit the data better. So we're going to move forward. So you're going to hit the stat button and now use the calculate menu, which is the middle menu. And I'm going to suggest that you go down to option 8. Now there is this option 4 that a lot of people use because it's more like the mx plus b, y equals mx plus b version of a line, the slope-intercept form of a line. The more statistically appropriate one to use is this a plus bx because the b's are going to relate to the betas in the model, and that's statistical notation. So option 8 is the one that is going to be more statistically appropriate, especially for a more advanced statistics class like this one. And I know this might be your first statistics class, but we're going to go pretty in-depth. All right, so when I do this, I get my regression statistics, so I get my line of best fit. And if you're not seeing these two things, then you need to turn the diagnostic on. So you hit second 0, catalog is above the 0 key, and you scroll down to diagnostic on, hit enter twice, and then rerun this regression and you'll be seeing it. And it's a one-time switch, so as soon as you've turned it on, you should be able to see the R and the R squared. And that's what we need. We need the coefficients to make our line of best fit, and we need R, the correlation, and R squared, which is called the coefficient of determination. So we need to make 3 analysis statements about regression. So the correlation is just going to give strength and direction based on the chart that I showed earlier. So here we have a positive 0.38. So that's between the 0.25 and the 0.5. So that is a weak positive correlation, right? Now the coefficient of determination is actually going to be used a lot because when we go to multiple regression, when we're using more than one predictor, we're going to see this capital R squared statistic a lot, and it's going to have the same interpretation. So what's the interpretation here? Well, we take the R squared value, convert it to a whole number percent, and that's the amount of variance in the Y variable that's accounted for by the x variable. Okay, so we're saying that 14% of the variance in y is accounted for by x. And in this case, we've inserted the variable name. So we're saying that 14% of the variance in pain, or the pain activity levels, is accounted for by the empathy score. The final one that we want to take a look at is the slope of the regression line. And so what this tells us is the change in y over change in x, right? So we know that slope from, ninth grade algebra, we had slope was change in y delta y over delta x. And so what we're going to do is we're just going to take whatever the slope coefficient is, and we're going to put that over 1. So I have 0.0083. Sorry, that's not the world's greatest 8. And put it over 1. And this proportion is exactly what we're trying to put into words. We're saying that for each 1 unit increase, right, as the x changes by 1 unit, then the y variable changes by this many units. Right, so that's the words we put down. For each 1 unit increase in empathy score, we expect a 0.0083 unit increase in these pain activity levels. So just remember that we're using this change in y over change in x idea of the slope, putting whatever the slope number is over 1 to make it a fraction, so I can, just write down this proportion in words. So that's what it means to analyze the slope of the regression line. And I want to remind you that correlation is highly dependent on research settings. So if you're in a physics lab or a chemistry lab and you're doing a Boyle's Law investigation where you're looking at the relationship between pressure, temperature, and volume, you definitely expect really strong correlations. If you got something like a 0.9, which in the social sciences would be incredible, almost too amazing to believe. Well, if you got something like a 0.9 in your Boyle's Law lab, you'd probably flunk because it's simply not strong enough correlation. You must have had some kind of measurement error. So be careful with always thinking a certain number correlation is strong or moderate or weak. Now, for the coefficient of determination, r squared, it's really useful. So this gives us a little more detail. So the correlation is a coarse measure. The r squared gives us a little finer detail. It says, all right, hey, we have about 15% of the changes in this pain activity variable being accounted for by those empathy scores. Okay, that's good. So we do have probably a significant amount of correlation. We're accounting for a significant portion, but remember there's still 85% of those changes in that pain activity that are accounted for by other things. Okay, so yes, we're doing well, we're doing okay. We're getting some association between the variables, but just remember there's a lot of other things going on too. And the slope analysis is really nice because it gives us an exact description of how the y variable is changing based on how the x variable changes. It's important to note that there are several synonyms, and most stats geeks use all of them at some time or another. The line of best fit, least squares line, prediction equation, the regression line, all of these mean exactly the same thing. It's the linear model that we're building, the line from the linear model that we're building, and we can use it to predict things. So we call it the prediction equation. So the idea is that we look at a scatter plot to make sure it's okay to start trying to build a linear model. We check the correlation and r squared, and once we know there's some kind of significant relationship there, we build and work with the linear model. So how do you know that the relationship is significant? Well, you don't have to guess. We actually have a way to modify the t-test, and we can check the significance of correlation directly. Like any statistical test, we have some assumptions for regression, and we have to make sure that the data actually meet the assumptions before we trust the results that pop out. The computer will spit out results. The calculator will spit out results. We have to make sure that there's some reason to trust those results. So the first one is linearity, which makes sense. If we're going to do linear regression, we've got to have some evidence of a linear relationship. And specifically, we have to make sure that some curving pattern wouldn't be obviously better. We don't want a nonlinear. We can do nonlinear regression, but if we're going to use linear regression, we need linearity. So the second one is normality of residuals. And what are residuals? We'll talk about that more in just a minute, but we have the Y values from our observed data. And what we're talking about residuals is we're comparing them to what we call the Y hats. That's what we would get if we plug the X observations into our line of best fit. We get an estimate of the Y, which won't be the same as the exact Y. So normality of the residuals, well, we can calculate Y minus Y hat, right? That's that's a residual, and we're saying that the residuals will be normally distributed. They'll have a bell-shaped distribution. Equal variances of residuals. Now this one's a little bit strange, but there's this line of best fit. And what they're saying is that the residuals, as they scatter around this line of best fit, right, that they'll be normally distributed. And if they don't have equal variances, you'd have really small variance of residuals here and maybe really large scattered out, where the residuals have much higher variance the further to the right you go, for example. So that's what we mean by equal variances of residuals. There's some really fun names. Equal variances is homoscedasticity, and when you have a problem with that, it's due to heteroscedasticity. But all we mean is that the variance is equal, whether you're using small x values or large x values in the model. The final assumption is independence of observations, and we, if you recall, have no way of checking that. That is a statistical research methods check that whoever collected the data needs to make sure that however they're measuring the variables, the measurements from one subject don't interfere or correlate with or correspond to or in any way interfere with any other subject's responses. So what we're going to do for linearity is we're going to use a scatter plot. And then for the other two in bivariate regression, we're going to check a histogram of the residuals. We'll have a hard time figuring out any problems with this equal variances. Even in the multivariate case, it's a little difficult, but definitely with just the tools on our graphing calculator, that's going to be one that defies us a little bit. But we're going to do the others and at least make an attempt to make sure that this model meets the assumptions of linear regression. Definitely take a look at this link. Some really good statisticians put together a really nice presentation with some graphics and explanations. Just as a spoiler alert, coming in Module 8, we're going to do multivariate regression, where we can have more than one predictor, more than one independent variable trying to predict this dependent variable. So our linear model is going to be better if we can use more predictors. And when we do that, then the QQ plot is going to help us check the normality, and then the fitted values plot will help us check linearity and the homoscedasticity assumption. So here's the promised details on the residuals. Okay, so I'm using an index because we say have, I think in this example we have 14 observations, 14 women and their significant other. Well, Y sub 1 is the first one who had the negative pain score, right? Pain activity score. Y sub 2 would be the second observation, the second subject, Y sub 3, and so forth. Now the Y hat is what you calculate when you actually plug in the x-score into the line of best fit, into that regression equation that we came up with. So y hat is the predicted value using the line of best fit, and y is the actual observed value. And a residual is just the vertical distance. So notice we're subtracting y values. So we're testing the vertical distance between the actual y and the predicted y. All right, well, we can do that, put it in a histogram, and check to see if the normality assumption of the residuals makes any sense. Let's see how that works on our graphing calculators. All right, so what I did was I made a note of my line of best fit. That's how I'm going to predict my y-hats. And then I decided to put that in L3. And so remember that if you arrow up until the list name is backlit like this, then you can type in a formula, which is what I did. It's a little hard to see down below. Oh, and there's a negative. Sorry, this is a negative 0.1, right? A negative 0.1. So sorry for the typo there. You can fix it in your notes. And when I type this in and hit enter, then I get this third column of data, and these are the residuals. Excuse me, I said L3 were the residuals. They're not. L3 are the y-hats. And L4 is going to have the residuals, right? L4, I'm going to take the y-hats are in L3, the actual observed y values are in L2, so then L4 is going to be the residuals. And again, you're just using the spreadsheet function on your calculator, arrow up to where the list name is backlit, and type in L3 minus L2, so that's second and the number 3 key minus second and the number 2 key. Hit enter and you'll have these residuals. And here's our plot of the residuals. And you can see that this is about as well as could be expected. We have taller bars in the middle. We do have a tail to the left and right. So when we go to second y equals and activate our X list is L4, right? We got to remember to make sure to point our histogram plot at the L4, which had the residuals. Now we're seeing a nice bell shape for the residuals, and the normality assumption seems perfectly fine. When the question is whether or not a correlation is statistically significant, we're going to use an adaptation of the t-test to determine the answer to that question. So we're going to look a little more at these formulas in the next video, but just briefly, this formula is true. Sorry. Right, that the slope is equal to the standard deviation of the y variable divided by the standard deviation of the x variable times the regression coefficient. And why is that important? Why do I point that out? Well, because we're running the hypothesis and trying to test whether or not we have evidence that the correlation is significantly different than 0. Right, so in the statistical model, we have a statistic, R, estimating a parameter, rho, right? Just like x bar is an estimate of mu, right? So R is an estimate of rho. So our null hypothesis is that the correlation is not significantly different than 0. And our alternative hypothesis is yes, there's some difference between the correlation and 0. But notice what has to be true up here, right? Standard deviations, because they're the variance, they're the square root of the variance, can never be negative. They can be 0, but they can't be negative. Excuse me. And as long as we don't have, let me think about this. Standard deviation could be 0 if there was no deviation. Yeah, if we had a trivial data set like 7, 7, 7, and 7, there wouldn't be any standard deviation. So yes, if there's any kind of reasonable data set, then these standard deviations will both be positive. So that means that the sign of the correlation has to match the sign of the slope. And if the correlation is significantly different than 0, then the slope will also be significantly different than 0, and vice versa. So we can also test this hypothesis, which is sometimes a little easier to get at. And this is beta is the slope significantly different than 0. So that's the logic of the test we're trying to perform. And we have this available on the third menu option on our stats button. We can go to tests, go all the way down to the bottom or close to it, and you may not have exactly the same letter depending on which model of the calculator you're using, but we're looking for this linreg t-test. Okay, when you pull it up, it has some options. Notice that it's trying to give you a beta like we have here and a rho like we have here. So they're trying to set up the alternative hypothesis, and we can just test that the correlation is significantly different than 0, or we can run a one-tailed test to see if we think it's greater or less than. You can save the regression equation. I haven't found that particularly useful, but that's what that option's for. So now the output from the linear regression t-test is pretty extensive. So you'll notice that you scroll down. Now the top 2 rows stay fixed, so you can see them over here, but we're getting new data. Right? Now what's cool is we do have the same data we had before. We've got the A and the B, so we have the line of best fit. This is the standard error, which is a new thing, but this is the standard error for the regression, which we need if we're going to do a t-test. We need a standard deviation value for the denominator of our t-test. And then we still have r and r squared, so we still have these available. The important thing about the t-test, though, is it gives us a p-value so we can assess the significance. It shows us the calculated test statistic, and it lets us know the degrees of freedom. All right, so taking a look at this, the p-value is 0.18, right? But that's larger than our 0.05 level of significance. So we don't find any evidence here that the correlation is significantly different than 0. So even though we had this weak correlation, right? We had this weak, nearly moderate correlation. Our sample size is so small, right? The sample size is so small that we're just not really able to say that there's a linear relationship here, that the correlation is significantly different than 0. I'll just let you know about the degrees of freedom. The degrees of freedom for regression is n-2. The number of observations of our data, -2. So there were 14 observations in the data, so our degrees of freedom is 12. Now, degrees of freedom is only really needed if you're running this by hand, and I'm just going to say that most authors of most stats textbooks will admit that if you're running regression, you probably need to do it with a machine, especially if you're going to start doing linreg t-tests and getting estimates of this standard error for regression. The machine-based models are much more accurate than the quick and dirty by hand methods. All right, so let's talk about a randomization approach to this. And I just want to keep pointing you to Rossman and Chance. They have created a bunch of stats applets, and I've provided a link. And I love their visualization, so I strongly suggest you go there. And you can just copy paste the values, or you can use the values that they have. But I'm just using their. Wait, no. I pasted in our values into the sample data, and then I clicked on use data, and you can see it's NS14. One of the things I love about this is they're showing the residuals as actual squares, right? So the vertical distance here, let me just switch the colors here. So the vertical distance here is the residual. That's the distance between the line of best fit and the actual data point. So what I've drawn in blue here is the residual, but we take the residual squared because we need to get rid of those minus signs. And what you're doing when you move around, when you move this line of best fit around, is you're trying to minimize the area of these squares. So I love that beautiful visualization of what it means to have a line of best fit according to the least squares approach, ordinary least squares. Then what are they doing? So a randomization approach, what they're going to do is they're going to shuffle, right? They're just going to randomly shuffle all of the y variables, all of the dependent variables. And they're going to shuffle them so that they get reassigned to different observations in the X variable. What's this going to do? Well, it's going to let us know how often you'd see a pattern like the one that we saw in the data, right? Where our slope was 0.0083, right? So I'm checking to see how often we're going to be beyond that mark. And so what the app does is allows you to do like 1,000 or 5,000 shuffles, and then it draws these lines where we get beyond 0.0083, either to the left, either below negative 0.0083 or above positive 0.0083. And then it gives us this estimate down here of a p-value, right? And so based on this, we'd say the p-value was 0.162, right? Which is where I got this. So the randomization approach is nice. It's called a permutation test. You just permute or shuffle the dependent variable observations into some new random association with the independent variable observations. And you see how often a pattern like the one we saw or something that significant or more so happens. The probability was about 0.16, about 16% of the time. That's not very unique, so we would fail to reject the null, just like with the ln-reg t-test on our calculator. Okay, just to summarize, that was a lot, but let's talk about the stages. The first thing we do is the verification, the first step of the verification, which is check the linearity, which means we scan a scatter plot to see if that idea is plausible. We can create a histogram of residuals. That's our second verification procedure that we need to run, but we can't do that until we have the line of best fit. In other words, we have to create the linear model first before we can assess how well the residuals fit the normality assumption. So we're going to have to wait on that. Our analysis of the model, we had this coarse analysis of correlation, slightly better understanding with the coefficient of determination, and then we have this precise relationship between the variables that's described by the regression line. Again, all of this is meaningful only if there's actually significant correlation, which we can test with a t-test or with the randomization approach that I just showed you on the Rossman Chance app. For our second example here, I'd like to run through things a little quickly, but again, a little more quickly than before, but give you a chance to see all the steps in action. Okay, so in the run-up to the 2018 election, the pundits were saying, Trump's political opponents were saying that, yeah, the economic indicators may be up, but it's only helping the wealthy. And that might be true. That had been true at times in the past, that the economic numbers looked good, but the people at the bottom weren't doing significantly better. It was just the people, the rich getting richer. So it's at least plausible on its face. And at the time, I was looking for real-world data sets, and I'd found some FBI crime statistics, and I found this median wages. And since we were in fall 2018, I was looking at this example the first time. I'm like, we can test this hypothesis. So what I did is went to the Bureau of Labor Statistics website, downloaded this data, and what you'll see is that we have this historic trend. So these are median U.S. wages since 1980. And, so 40 years or more of data. And here's what we found. Obviously, the linear relationship is very significant, but we find that weekly wages are increasing by about $4.05, $4.04 per week. That's a weekly wage, and that's increasing per quarter. So each year, a person's wage is going up about $16 a week. And you'd multiply that by 50 to see what the annual wage increase was, which I think is $800. So that's the historic trend. So we're going to compare what happened in the Trump administration. So here is the data. Okay, and I also noted how many earners there were. So you can see that the number of earners had grown and the median is also growing. Okay. And I just used, instead of actually putting in, time, this is quarter 1, 2, 3, and 4 for 2017. I just called them, what you can do for this analysis is just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, down through 12. So in your calculator, you just need these equally spaced intervals. All right, that's what I mean by use the time periods. Okay. So we put this in our graphing calculator and we have some results. So yes, there appears to be a linear trend. Yes, there's some wobbly data down here. Okay. And this is a slightly seasonal measure. So there is a little bit of sort of a sine wave kind of pattern that will develop. Because there are certain times when more wage earners are out there, like for instance in the fall when there are sharecroppers, wage earners who don't work all the time, but they work during the harvest season, for example. But anyway, this seems like a linear model is possibly appropriate. And here are the regression statistics, and here's what I want to take a look at. Right, I want to take a look at this slope number, because during the Trump administration, they're making about $6.90. Now, I don't know exactly what's wrong here. I think it might be this data point, and I go over this in the notes where I do this in our studio, but I believe the correct value is $6.19. All right. And again, I've double checked the one I did in our studio. So sadly, they don't match. I'm not quite sure exactly what's happening. I'm going to continue this one just so you see how to do it with these data, right? If I put these data in, I should get this. Let me look. Yeah, I'm going to have to double check why there's a difference. Okay. And so notice that we have a correlation of 0.95. We have a very strong R squared, so 91% of the variance in wages is accounted for by the time period. And we have this value. And of course, the significance using a t-test is strongly suggestive that the correlation isn't zero. But we didn't care whether or not the correlation was zero. What we cared about was the correlation significantly different than the historic trend? Right, that's what we care about. So let's take a look at that. And this is why I brought this example up, because we can use a confidence interval instead of a LinReg t-test to kind of get an estimate about what this slope actually is. Okay, so this option is right below your LinReg t-test. And what it does is it spits out a confidence interval estimate for the slope, which is about, on the low end, $5.38 up to $8.41. The key thing is that the interval does not contain this 405, so we can reject the null at the 0.025 level. Why, when we use the C level, or we ended up with alpha equals 0.025? Well, remember, we have this bell-shaped distribution, and this confidence interval, right, is going to cut it off where there's 95% in the middle and a symmetric amount on either side. So I'll end up with 2.5% of the area under this curve to the left of this confidence interval and 2.5% to the right. And this matches up, since we're doing a one-tailed test, this matches up to a significance level of 2.5% or 0.025. And evidence suggests that in the Trump area, the median wage growth was higher. Well, why median wage growth? That might be a question. Well, so remember, in our exploratory data analysis, we know that the mean is very sensitive to outliers. So what you'll find in these in economic data sets is that the outliers to the right, the outliers to the right, the incredibly wealthy people, the tech billionaires and the oil magnates and the sheiks, the people who are extremely wealthy, their wealth brings the mean way up above the median. So we'll have a skewed right distribution. So the median is going to be a much better measure of how a typical wage earner in the US is doing. And in the RStudio notes, you'll find that we also have the 10th percentile and the 25th percentile for wage earners to look at. Now that data only goes back to 2000, but still we can compare and see if there's a difference. So we can also maybe argue from the left, and they have, pundits on the left said, well, Trump inherited the Obama economy. His economic results are just riding on the coattails of the 3 years under Obama. Well, that's plausible on its face. Let's take a look at that. So now we have the Obama administration, same thing, the last 12 quarters of the Obama administration. And I know that Trump was elected at the end of 2016, so Trump's election happens in November right here, but he wasn't inaugurated until January 20th. So I've put the first quarter of 2017 as the first quarter under Trump. And then even though the election occurred in November here, this is the last quarter for Obama. And hopefully that's okay. And so you can go through and verify these statistics, but notice what we found is that the average growth in the last 3 years for the Obama administration was about $5.08 a week. If you run LINREG T-interval and compare this to the historic trend is in the confidence interval you'd make for the Obama data. But the Trump era growth rate is significantly different than both the Obama and the historic growth rate. So take that for what it's worth, but that's how to use a confidence interval as a hypothesis test. We can actually build a 95% or 90% confidence level around the slope, and then we can compare it to other values to see whether or not those values are likely to be inside the confidence interval or not. If they're not likely to be inside the confidence interval, if they're not inside the confidence interval, then we reject the null. So I do want to give you some caveats. Agenda-driven geeks can definitely lie with statistics. All kinds of people like to lie with statistics, especially politicians, and our media has become very agenda-driven, both on the left and the right. So what I want you to know is that in a class like this, I want you to be able to detect other people's lies, right? So be able to check the assumptions, be able to understand where problems might occur. And so one thing you might come up with this analysis, you're like, hey, you were doing the median wage. There's other ways of earning money. You know, people in the gig economy, are they wage earners? Well, probably not. We could check the data set and see. So they'd be subcontractors, people on commissions, real estate, investing. All of these kinds of income aren't really measured when you're talking about wage earners. Also, there are lots of different ways of assessing the economy, including GDP and the stock market and lots of other indicators, including jobless rates, unemployment, whether unemployment's going up or down. So definitely be aware when you hear somebody pushing an agenda and quoting statistics. We want to learn to be smart about that, and we want to be the savvy geeks that are able to detect when something's wrong or implausible with somebody's argument. But statistically, what I want you to know is that these model statistics we get, so the line of best fit, it's robust with respect to violations. Excuse me, not the line of best fit, the model statistics. So R and R squared. R and R squared are robust. It means they'll retain their correct values under stress when the normality assumption is violated, right? Now, nothing is robust with respect to the linearity assumption. If you violate the linearity assumption, nothing's going to be right. But R and R squared will hold up when there are violations of the normality assumption. And The problem is, though, I can't use these t-tests and t-intervals if there's a violation of the normality assumption. But that's why I showed you the randomization approach. There's a really cool, or I talked about it. In the RStudio notes, you'll see a couple different randomizations of that we can do when the normality assumption is violated. So those are the key takeaways. Just to know that regression is an extremely helpful tool. Just make sure that you're applying linear regression to something that's actually linear, and then you can trust the regression statistics and line of best fit. What you don't want to trust, though, are t-tests and t-intervals unless you're pretty sure that the normality assumption's okay. If it's not, then use a bootstrapping approach or a permutation test. I know that's a lot to take in. Thanks for hanging with me, and definitely check out the RStudio notes. I think they're very well done and will help explain exactly what's going on. And instead of having to use some clunky things in our calculator to check normality and linearity, we'll be able to generate those plots with just one command and get all the diagnostic tools that we need. So I think it's a lot easier to do in RStudio, and I hope you take a look at that material very carefully.